Good evening. สวัสดีครับ We still have seat available at front. Perhaps students can come to sit at front to see the good presentation for tonight. Oh, should I ask student one? Okay, dear member and distinguished guests, right, good evening for tonight. My name is Anupong Chailet. I'm SPE Thailand Board of Director. I am your part-time MC for tonight. I'm together with Kun Panit, our SPE board for life professionals. On behalf of SPE Thailand Board of Directors, I would like to welcome you to SPE Thailand Technical Meeting for tonight. Thank you for being here tonight, and we are happy to see many oil and service company, government representatives, and academia from the upstream oil and gas industry support our event. Also, a special welcome our students. Please raise your hand to show your hand, please, student. Okay. Anyone raise your hand? Bring your hand to front table here. ข้างหน้าว่างครับมา
เนี่ยมาตัวนี้เลยครับ
มาข้างหน้าเลยครับ
โอเค
Okay, thank you นะครับ student. Okay, before we continue our program, please take note of this safety announcement. There are no emergency drill for tonight. So in case of alarm goes off, please remain calm. Right. Look for the nearest emergency exit, which are all clearly marked here. From there, the hotel staff assigned to this ballroom will guide you down to the stair and assembly point outside. It is important for everybody's safety. You remain calm and don't rush. Right. Here is agenda for tonight. Right, we starting from section announcement, presentation, Q&A, and closing remark, and definitely lucky draw for tonight. These companies are the sponsor who support us, our Thailand monthly technical meeting for the seasons. For any of you who may have just tuned to this meeting, if you would like to see your company name in here, please reach out to us. We appreciate your support, and of course, our society needs you. At tonight's event, we hope to show you how our industry continues to create and innovate to meet our future energy needs. The industry here in Thailand is unique and perfectly fit the SPE mission and vision. We network and we share. Thailand section valid membership as of today. Now we are at 580 members. This is combining the 338 professional and 242 student members from Chulalongkorn, Suratnari, Prince of Songkhla, and Chiang Mai University student chapters. However, we still have around 151 professional members from 2023 who has yet to renew their memberships. May I remind you to please recheck your membership status, and if lapsed, please consider to renew it for our society and sections. And to all of us, please invite a colleague to join our meeting, or even better join SPE, because we always need new members. SPE Thailand is still the largest professional oil and gas industry organization where you can regularly meet and greet in the relaxation environment. And the benefit for SP membership that I will not read through everything, and of course, if you register for our event for tonight, you get free beer, wine, and nice dinner. And networking, of course. Okay, come to main course for tonight. Ladies and gentlemen, I would like to invite Kun Phanit, our board of directors, to introduce our speaker for tonight. Now our industry promote the dual role, not only live professional. He still need to introduce our speaker as well.
Thank you, Kap. Sorry, I think we got minor miscommunication, but I will try to do our best. Good evening, everyone. My name is Phanit Jesadawaranun. I am one of the chairperson for technical program as well, and of course, glad to have all of you here. Smiley face and enjoying wine. That's a good start for tonight. Let me give a quick introduction for our speaker, Kundev Turner. Kundev Turner is Asia Pacific Region Director for SeekOps, based in Kuala Lumpur, Malaysia. He started his oil and gas career as a wildlife engineer, same as me. After completing his mechanical engineering degree and working the field for 5 years in locations across Middle East, he then held various operations, sales, technical management position in upstream services product line in Vietnam, Malaysia, and Angola. Then he returned to Malaysia. He specialized in compliance risk management before entering the methane emission detection field in SeekOps. Kundev is UK chartered mechanical engineer. He holds an engineering degree from University of Wales, Cardiff, and he also got an MBA from Imperial College London. Ladies and gentlemen, please welcome Kundev Turner from SeekOps. Thank you. You don't have to stand here.
I can walk around. Thank you, Kun, for the kind introduction, and thank you to the SPE Thailand section for their kind hospitality so far. I look forward to some of the free wine later. I'm going to try standing here to start with at least. So, good evening, everyone. Thanks for coming along this evening. It's a great turnout. I didn't expect quite such a crowd. I can't see most of you because you're so far away, but thank you for turning out tonight. And I hope it was an interesting session. Maybe a little bit different for some people. It's not traditional oil and gas stuff, and we're kind of in an evolving space here, so it might be interesting for some. So the topic tonight is methane emissions detection and quantification. Top-down methane. I'll come on what top-down means, and we'll focus on offshore as well, because there's some particular challenges with offshore measurement, and it's also very relevant, of course, to the Thailand market, where there's a lot of offshore infrastructure. Very briefly, SeekOps is a startup spun out of NASA JPL about 6 or 7 years ago to commercialize a bit of methane sensor technology, and we've developed that sensor into a lightweight sensor that can be conveyed on a drone, and the associated methodology to fly that sensor and to analyze the data. So that's what we do. The talk this evening is going to be fairly high level because of the mixed audience. So I'll try to do a kind of a broad overview of methane emissions measurement and how we go about it, and what the challenges are, and what the kind of current state of technology in the industry is, and what the drivers are. So this is the outline of the talk. So setting the scene, and I think many people should be familiar with the first one. Why are we measuring emissions? Why methane in particular? And I'll delve into a little bit about how we do it, what the challenges are, And then the rest of the presentation will be on the technology, diving into the broad technology, and then we'll finish up the second part with based technologies and also how they might apply here in Thailand. So just point out, there's an important word appearing on this slide, which is quantification. So we're not interested only in finding emissions, detecting emissions, but we're interested in quantifying the amount of those. And I'll dig into a little bit about why this is important and why it's a big step from simply just detecting gas. But we should get up fairly quickly and have plenty of time for some discussions and questions at the end. So first up, why are we interested in methane emissions? And I hope there's nobody in the room would debate that emissions are having a climate effect. And if there is, I'm happy to have a discussion after over a beer. But it's clear that we need to do something about emissions and try and control the effect on the climate. The trend is very clear. 2023, the average was over 1.5. So we're getting close to that 1.5 limit that was set by the Paris Agreement. And so there's action needed. A lot of focus, of course, is on CO2 as the main driver of global warming and climate change. We produce vast amounts of CO2 in our day-to-day lives, so there's a key focus on reducing our emissions of carbon dioxide. Methane, on the other hand, is another gas that we emit in lower quantities, but it's massively more potent as a warming gas than CO2. Over a 20-year time frame, it's about 80 times as effective at capturing heat and trapping it in the atmosphere. So there's some good news there, is that methane has a much shorter life in the atmosphere than CO2. So typically in the order of decades rather than centuries for carbon dioxide. So if we can reduce the amount of methane we're emitting, we can quickly reduce the amount of methane in the atmosphere and therefore the climate effects. Because methane is so potent, it's really driving the rate of climate change. So about 30% of our current temperature rise can be attributed to methane. So if we can cut methane emissions quickly, we get a quick response of methane concentration in the atmosphere, and we can slow down the global warming effect. And that gives us more time to work on the CO2 problem, which is a more difficult one. So there's plenty of anthropogenic or man-made methane emission sources. The big ones are oil and gas, coal mining, agriculture, and waste. About 40% of the man-made emissions come from oil and gas. About 90% of that 40% comes from upstream and midstream sources. So more good news there is that those upstream and midstream sources, we know exactly where they are, and we know exactly what we need to do to fix them. It's just a matter of money and investment. And then another bit of good news is that most of those emissions can be fixed or can be eliminated at basically no net cost, because this is gas escaping to the atmosphere, so it's our product. So about 70% of those emissions can be eliminated, with some profit on the side. So I mentioned quantification. It's long been possible to detect trace gas. The challenge we're facing now, and the bigger technical challenge, is quantifying how much those emissions are. And the old saying is, what doesn't get measured doesn't get managed, and this is a classic case of that. And if you ask a typical asset manager, they would view this kind of measurement as just a cost. It's just money spent and there's no value back. But especially these days, there's an increasingly strong set of genuine business drivers behind this. The first one, of course, is emissions represent lost product for us. Methane is the core component of natural gas, so that's natural gas, that's a product going out to the atmosphere. So if we can find where those emissions coming from, we can find the bigger emissions, and we can prioritize those and maximize the repair dollars. So the return on that remediation is much faster. But then there's a multitude of small leaks from valves and seals and all over our process facilities that add up to a massive amount of methane emissions. I can put a number to that. So SeekOps is a relatively small company. We've got a global operation, but we only have 36 people, 6 pilots out flying drones. And last year we measured and we quantified 475,000 tons of methane emitted. So calculate that out, that's about 4.5 million barrels of oil equivalent of emissions measured just by us. And that's, I don't know what fraction of the global emissions that is, but that's it's a small amount. So you can imagine the number if you consider the total amount of lost product going out just to emissions. There's an increasing raft of legislation and regulations appearing. 155 countries have signed up to the UN's Global Methane Pledge, which is a national commitment to reduce their national methane emissions significantly, 30 to 50%. And this is starting to flow down into national regulations. So governments are pushing this into industry. So that's driving a whole raft of new legislation. And there's some pretty big sticks appearing in the market in the more advanced economies where they're getting ahead of this. In the US, for example, the EPA is now implementing the rules that came out of the IRA methane reduction program a couple of years back. And emitters now get penalized substantially, $900 a ton of methane emitted, rising over the next 3 years to $1,500 a ton. So that's a big penalty to pay. We can see the carbon border adjustment mechanism coming into force in the EU. So that'll be charging importers for the carbon footprint of the stuff they're bringing in from elsewhere. That's going to include the methane emissions associated with LNG or anything else which is using that gas as an energy source. So that tentacles of that will spread globally. In the region here, Australia has what's known as the safeguard mechanism. So they have a cap of emissions, and if emitters go above that cap, then they get penalized, and that cap is reducing year over year. So they're starting to squeeze that down. So those kind of sticks are starting to appear everywhere now, and I think we can only see that expand. There's a number of global frameworks appearing to help measure the emissions on a consistent basis. From the oil and gas industry's perspective, the biggest one and the most influential one is OGMP 2.0. That's the Oil and Gas Methane Partnership. Now, this is run by the International Methane Emissions Observatory in the UN, and it's basically a standardized framework for operators to measure their emissions and then subsequently manage them. And about a little over half of the global oil and gas production now is captured within companies who've signed up to the OGMP2. Right now, it's a voluntary framework. It's going to become increasingly strict as to what's required. So OGMP is really driving a lot of the methane quantification business. There are some carrots as well as sticks. So particularly in the region here, we've got Japan, we've got Taiwan, we've got South Korea as big LNG markets. They're very heavily reliant on imported LNG. And as part of their effort to decarbonize their energy system, they're starting to look at how they can make that LNG as clean as possible. So they're looking back along the whole supply chain from wellhead through to delivery and helping the suppliers to implement emissions management programs so that they can assure that gas is as clean as possible. And they're willing to pay a premium for that. So there is a premium price on that clean gas. In the US, we're starting to see organizations like MIQ who are putting together very robust frameworks for certifying gas. So if a buyer wants to buy the cleanest possible fuel, then they can buy a certified gas. And then finally, and everyone's well aware of the public scrutiny that the oil and gas industry gets. Our license to operate, we have to show that we're doing our best to operate as cleanly as possible. And the public's also very well aware of methane now, and I think everyone probably saw the hype at COP28 in November about methane and the noise that was made. So it's very much in the public eye. And the other thing is we're positioning gas as a clean transition fuel, but that only holds water if we can demonstrate that we're producing the gas as clean as we can. So emissions management is a big part of that. So those are our business drivers. Digging down to a little bit about how it's done. So let me just set the scene a little bit. We're not talking about gas detection here in the HSE sense. So these gas detectors which are installed on basically every facility for safety purposes to measure leaks. So that's a different business, and those sensors are measuring in the percentages of LEL range, so quite high concentrations of gas. we're looking at emissions. So emissions typically are high volumes over a long period of time, but extremely low concentration. So 20, 30, 50 parts per million of concentration in the air. So well outside the range of traditional gas detectors. When we're looking at emissions in particular, there are kind of two categories of emissions measurement approach. One is known as bottoms up, one is known as top down, and that's not some kind of drinking game, that's a real thing. So bottoms up is the way it's been done traditionally, and that's a matter of either measuring or calculating the emissions from each individual component in your process. So every flange, every valve, every compressor seal, you count up how many you've got, you measure them if possible, and then you add all of those little emissions together, and that gives you a bottoms up total of the emissions for that facility. And this has been done for a while as part of LDAR, leak detection and remediation programs, which is an important part of asset integrity work. So this is done on an ongoing basis, just to keep on top of the process health and make sure it's operating safely. But if you want to do a full emissions calculation for a big facility, then it's a lot of time, it's a lot of work to measure each and every one of those little emissions. What I'm going to focus on today is what we're calling the next generation, and that's known as top-down. So this is looking at a facility or an emitter remotely and attempting to quantify the emissions from that facility from a distance. So not measuring by hand, but stepping back and trying to measure the totality of the emissions. Those people who are familiar with OGMP will know that as level 3 and level 4 is bottoms up, and then level 5 is top down. The OGMP 2 tries to reconcile the two, so the bottoms up measurement, top down measurement, and they should match, and that gives you a good idea of the quality of your measurement. If you've got two independent measurements of your emissions, they should match up. So it's a bit of an intractable problem. Methane plumes, and this is what we're looking at, is the plume of methane that's coming off an emitter. So you imagine a cloud of smoke coming off a bonfire. It behaves in much the same way, except it's totally invisible, and as I said, typically very low concentrations, parts per million of methane. And they don't behave in a very predictable way. They move with the wind, they move with the nature of the source, they move with the temperature. So knowing where that plume is and what shape it is and how it's behaving is difficult to do, and there's a whole branches of atmospheric scientists working on exactly this problem. Oil and gas emissions can be continuous, they can be intermittent, can be somewhere in between. They vary with production rate, they vary with valve settings. So they're up and down on a daily basis. They vary with atmospheric pressure. So the emissions do vary. Some are quite constant. A gas turbine exhaust, for example, with unburnt methane is relatively steady, but a vent on the process might be up and down with the production rate. We're looking at offshore today, and offshore brings some particular challenges for emissions measurement. One is down to the physics of the measurement, how we actually do this, and pretty much all of the ways of measuring methane in the air, trace gases in the air, use an absorption technique. So we're looking at the wavelength at which methane, and any molecule will absorb a particular profile of energy, and in this case we're looking at infrared light. So we pick a wavelength of infrared light that's specifically absorbed by methane and only methane, and then we measure the attenuation of that. So the physics is fairly well proven. A lot of the sensors are using reflected infrared light, so either sunshine, reflected natural light, or a laser projected from the sensor, which is coming out and it's coming back from the background. The problem of being offshore over water is all that infrared light disappears into the sea, and you don't get a reflection coming back. So none of that kind of sensor work over water. So that suddenly restricts what you can do in that environment. The other thing about offshore is the nature of the facilities themselves. They tend to be densely packed with equipment. They tend to be tall and thin with flares on top, and so everything is kind of packed and tall. So that makes it more difficult to measure because you've got 3 dimensions to look at. And then, of course, typically offshore installations are better built, they're better maintained than onshore facilities. So the emissions are lower, which is great, but it does make them harder to measure because they're always a bit lower. And then the last thing really is that, like a lot of things in oil and gas, a lot of the technologies have been developed in US land, so you bring them to the international market, they don't work quite as well as they could. So a lot of particular challenges to offshore, and I'll come back to it again. And the final challenge is, this is a relatively new field, the top-down measurement approach, and there's a lot of new technologies appearing, there's a lot of new regulations appearing, the standards to describe how it's done are not very well formed, so there's this kind of uncertainty in the way things go, there's a lot of lack of knowledge, so it's an evolving field, so it does have a lot of challenges for somebody who has to sit down and design an emissions measurement program. I'll dig into the technologies more on the following slides here, but I'll point out a few key differences in what we're looking at with the different kinds of technology. So, I'll jump into these, but satellites, for example, through to drones, through to fixed sensors, these things are working at different scales, completely different scales, both temporally in time and also in space, in distance. So, a sensor which is taking a snapshot every time it flies over is giving you an intermittent measurement, maybe every 2 weeks, maybe once a year, and it's going to give you a different answer to a sensor which is sitting and measuring on a continuous basis. And so the emissions are up and down, so you're going to get a different answer between different time scales. And then, of course, a satellite has got a very big view. A drone has got a very small view, so trying to reconcile those two different kinds of data in a kind of sensible way can be very difficult to do. The performance varies wildly, and I'll dig into this in some detail as to how much gas can they see, how big an emission can they see, how accurate are they, a lot of performance characteristics of the sensors which make it, again, difficult to compare the data and use it in an integrated program. There's a lot of new technologies appearing. Some of them have got a sound scientific basis, some of them don't. One of the challenges with this kind of technology is if you go offshore and you do a measurement, you get an answer, but there's zero way to check that, really. So the only way to be confident that the measurement you've made offshore is any good is if that technology has been very well proven in a controlled environment. So we do a lot of controlled release testing where we have known emissions of methane, fly the surveys over and over again to build that confidence that it actually does work. So when you take it offshore, you've got a result which is consistent. And then finally, it's probably fair to say the state of the technology is such that there isn't a single solution that gives you the whole answer. So typically a combination of the different technologies is needed. So that's another challenge, is picking that combination depending on what your objectives are for accuracy, volumes, and so on. So different customers, different fields will have different ideal solutions. So it's not easy to put together the mix of technologies. So digging now a bit more into how it's done. And I've got kind of 4 major categories of measurement technology types here. There's a 5th one which is not included, which is shipborne sensors for offshore, but they're still very much in the research category. They're not really a commercial solution yet, so I've not put that on here. So these are ordered pretty much in order of scale. So of course, satellites, this ubiquitous now. Particularly, methane has gotten a lot of focus. So for a long time, there's been kind of general purpose atmospheric satellites up, Sentinel, and so on, which could see the very big methane emissions. But now there's an ever-increasing number of methane-specific satellites up. There's a company called GHGSat who do commercial emissions measurement. They have a constellation of 9 specific satellites. They can see a swathe about 2 kilometers wide with a reasonable degree of accuracy. They're about to launch another 3 satellites, which will give them the ability to come over every 2 weeks and survey a site. The EDF, the Environmental Defense Fund, very soon are launching their methane sat. It's gone to SpaceX this week. And that's basically going to be a spy in the sky, a very high performance spectrometer, so it can see relatively small emissions, and they'll be just watching what everyone's up to. They've signed a deal with Google to publish that data publicly, so that's going to be a name and shame deal. That's the EDF's thing. And there's a couple of others in the pipeline as well. So there's more and more spaceborne observation. So they're very important in the whole thing because they have that wide view. They can see over borders without going through the hoops to get permission. So they can do that global view. Disadvantages that I mentioned already, they don't work well over water. They're using reflected light techniques, so typically just sunlight. So that doesn't work if there's water, or if it's cloudy, or if it's dark. So that very much limits what they can do in an offshore environment and a tropical environment. So not great for this type of application. And they also have a pretty high threshold for what they can see because they're far away. They're looking at emissions in the order of hundreds of kilos per hour of emissions of gas. So quite high. They can see the big stuff, the important stuff, but not the kind of day-to-day emissions you'd get from a typical facility. Closer to the ground, light aircraft. This is a very successful application in North America, a big land area with lots of dispersed facilities. Doesn't work very well in this kind of environment. It's using light aircraft, manned light aircraft offshore day to day isn't a very popular solution. Difficult to mobilize, it's expensive, and the same challenges over water. So light aircraft in an offshore environment really aren't a thing. Drones we'll talk about in more detail. Of course, with the drone you can get right into a facility, and drone services in all industries, but including oil and gas, have become pretty day to day now, and we're using them all the time for inspection, for imaging, and so on. So everyone's comfortable with what to do with the drone, how to operate it. There's a lot of good drone companies around who can do this kind of service. So the availability of drones is cost effective, and because we can get close, we can pick up emissions in the order of grams per hour, about 20 grams per hour. So essentially, you can see almost everything that's coming off a facility. Right now, it's still visual line of sight, so the pilot has to be able to see the drone is the typical application, which means you have to send a crew offshore or have a crew on a boat nearby so that they can fly the drone within sight of the facility. So you've still got then all the hassle of training, POB, and what have you for offshore operations. So one of the holy grails is VV loss, or beyond visual line of sight, so you can launch the aircraft onshore, fly it offshore, do the work, and come back. And we've done that in the North Sea. It's possible technically, but there's a lot of regulatory challenges, and how does it integrate with the aviation environment? So BV loss is on the cards, but it's not coming immediately. And then the final category of sensors here is fixed sensors, and that's exactly what it says on the tin. These are sensors which are mounted on the facilities, and they come in a variety of different types, different measurement techniques. Some of them are using just metal oxide sniffer type sensors, all the way up to very sophisticated laser camera devices which are able to image the methane plume. So a variety of different options here, and the big plus for a fixed sensor is it's there all the time, so you get that constant measurement of what's happening on the facility. The big minus still is that they aren't very well proven for quantification. So they can see the emissions, but it's the maths to quantify isn't proven yet. So they're a little bit uncertain. Plus, you have to install them offshore. They have to be calibrated. They have to be maintained. So there's a bit of a constant cost behind them there. But that constant measurement is very valuable. So if you have to choose a technology to use for your methane emissions program, what parameters should you consider? How do you tell if something is good or not, or suitable or not? And the first thing to think about is what do you actually need to do if you're designing a program? What parameters do you need? So just like everything, you don't spend more money than you need to on something which is over-spec'd. So designing the program objectives is the important first step, and that leads you on to then deciding on the technology to use. And I've picked out 4 or 5 key performance parameters here, kind of ordered generally in order of significance. I'll dive into these, but quantification uncertainty, how close is the result you get from the measurement to the reality? The detection threshold, I've mentioned a couple of times, how big an emission can this thing see? And related to that, the probability of detection, and this really applies to aircraft and satellites, which are quite far off. Will they see that emission at that size or not? Offshore, I've mentioned verticality. We've got that third dimension of emitters from below deck level all the way up to the flare. Can you see that third dimension with the methodology? And then lastly, how closely can that measurement tell you where the emission's coming from? What's the source of it? So quantification uncertainty is probably the single biggest kind of academic topic around this at the moment. Is how do you tell how close that measurement is to reality? And we've got a whole department of atmospheric scientists working on uncertainty calculations. How do you tell what that number is, and then how do you minimize it? So when you're trying to reconcile a big emissions program, you have all the uncertainties, and you have to know how to add them up. So it's a very important thing, and because it's such a difficult measurement, the uncertainties can be very high, in the order of hundreds of %. So you get to the point where the measurement is basically useless because it's got a 400% uncertainty on it. So all of these kind of technologies essentially start by measuring methane concentration in the air, and then the wind, so the airflow. Those are the two key data inputs. So to turn that wind and that methane concentration into a methane flow rate, there's an amount of processing needed, and that's really where the uncertainty comes from. So there's a degree of uncertainty in the measurement itself, depending on the type of sensor it's using. That varies a bit. There's quite a bit of uncertainty in the wind because of turbulence. It depends where you're measuring the wind, whether you're at ground level or up in the sky, or if you're using meteorological data. So the wind itself brings a significant chunk of uncertainty to the inputs, and these things stack up. So as you do your processing, and it's different ways to do that, then these uncertainties do stack up. So sometimes you spit out these very high uncertainties. So that's the biggest academic challenge for this whole thing, is knowing what that is and understanding what the sources of uncertainty are. Different ways to do this processing, different principles. Some use assumptions and so on about the plume, some are more direct, but they all run into the same kind of challenges. So that's the first question to ask when you're looking at a technology, is how uncertain is it? The detection threshold is relatively straightforward to understand. What's the smallest leak that this technology can see? And I've already touched on the difference between the different scales. So it's kind of intuitively obvious that a satellite can only see big ones, whereas the drone can see quite small ones. And this is important to know when you're planning your emissions program, is to, are you going to capture all of the emissions, or are you going to capture only significant ones? And kind of associated with that is the probability. So if we specify 10 kilos an hour as a threshold, is that 10 kilos an hour at 10% probability or 90% probability? Obviously quite different things in terms of how many emissions at that level you can expect to see. So I don't know if you can see this plot. It's quite small, but this is real data from the US. So this is about 1,000 sites onshore, consolidated, and we've on the x-axis here is the number of sites, up to 400. On the y-axis is the quantification amount. So 0 at the bottom, up to 1,000 kilos per hour at the top. So at the bottom, you can see there's about 100 sites which have 0 emissions. So only 10% of the sites measured here had nothing. So 90% of all the facilities were emitting something. And that's about right. We very rarely fly a facility that doesn't have any emissions at all. It's particularly offshore, where there's a flare and a vent and so on, there's always emissions. So drone threshold here about 0.02. So everything above that threshold can be measured. Everything in the space between aircraft and drones is missed by the aircraft. We go past the aircraft, and there's another chunk here up to satellites. So you can see where the distribution is and where a lot of the emissions fit, and they're all quite low. So you need to be aware of that and know that you have to see emissions down at that kind of level. The EDF have done a study of the same kind of thing, and they reckon that about 50% of all US emissions are less than that kind of 10 kilos an hour threshold for the aerial solutions. More data here, and this is kind of illustrating the verticality point. This is about 16,000 individual emission points that we've measured globally. And so along the bottom is the altitude. Where do we find that emission point? Up the side here is the the emission rate. This is in scuffs per hour. So you can see there's a big chunk down low. That's all the land-based stuff. Everything's kind of at the same height. And then when you start to look offshore, there's a significant chunk are up at the kind of 120, 140 meter altitude, so way up. And this is typically vents and flares and so on, the stuff which is high up on these big facilities. So you can see there's a big chunk of the total emission is up high. So you have to be able to capture that third dimension to see everything. And then the last one here I've picked out is localization. I'm not sure if anybody recognizes the facility, but this is a typical offshore facility, a big one, multiple potential emitters on a site like this. The obvious ones we always look for, the flare, of course. If you've got vent stacks, they'll typically always be emitting. The flare will always have unburnt methane in the exhaust, anywhere between kind of 80 to 90% efficiency, so there's always a bit of methane left over. And then gas turbine exhausts, same thing. They don't burn completely efficiently, so they're always leaving a bit of methane in the exhaust. So those are the sources we look for. And then, of course, there's all the fugitive emissions from the process itself, all the tiny emissions coming from the seals and the valves and what have you. So that's coming off the process decks. So the closer you can pick out those individual emissions, the more effective you can be at then going in and fixing them. And if you can pick out more or less where that is, then you can send your LDAR crews in with the handheld instruments, the kind of measuring individual components measurements, and get to the source of the problem much quicker. So that saves cost, and it also allows you to mitigate much faster. So being able to kind of zoom in and kind of locate where that emission coming from is a very useful feature of a measurement. And typically you've got to get closer, so fixed sensors and drones to getting close enough to see those individual emitters. So I want to talk a little bit about the specific technology, drones, because this is quite an applicable one for Thailand. It's a cost-effective way to survey a lot of facilities, and Thailand's got, as you guys know, many offshore facilities. So to survey all of them is a fairly major task. So we're looking for something which is going to be quick and relatively cheap to be able to get on top of those and see which ones are emitting, focus our efforts at remediation on those particular ones. So this example, this drone is a typical commercial drone, a DJI M300. DJI are by far the world's leading drone builder, and this is the M300. This is a very well-proven commercial drone, so everyone uses the same aircraft. This part in the front is the sensor, and this is a super sensitive methane detector. This measures down to parts per billion. 10 parts per billion is the measurement threshold. And to try and put that into context, I figured this room is about 750 cubic meters. So 10 parts per billion in here would be 7.5 milliliters of gas, of methane, dispersed throughout the room. So it's about half a spoonful of gas in this room is 10 parts per billion. So we're looking at very low concentrations of gas. And you need to do that because the background methane in here is probably 1 or 2 ppm. So you have to be able to measure that so you can subtract it from your final measurement. So you have to be working at those very low concentrations. And what we do with the sensor is use it to fly a particular downwind flight path, and there's an illustration here. It's got kind of a zigzag through the methane plume. We're trying to map a slice through the methane plume by concentration, so we can kind of take an image of what that methane plume looks like. So that's how we do it, and sometimes it's an L, sometimes it's a flat plane, but as long as we're capturing that methane plume, we can then use that as the input for our calculations later on. At the same time, measuring wind. The drone itself is measuring wind, and we're also capturing high-resolution vectors on the ground as well, so it's inputs to the wind data model. And the advantage of this is you can get close enough to the facility that you can see individual methane plumes, so you can measure the flare directly, you can measure the turbines, you can go to the process deck and you can have a look around for individual methane plumes to see what's what and identify them and measure them independently, because you can get pretty close. I've got a video of what this looks like at the end of the presentation here to give you a sense of how it's done. So this is a case study from Southeast Asia. It's a little bit maybe complex, so I'll try and talk through it. So the picture on the left here, this is a top-down image of a platform, and this case is a gas platform, high-pressure gas wells. It's got gas pneumatics, so it's using the produced gas to operate the valves and everything on the facility as the source of energy. So always if you've got gas pneumatics, because the gas is being used, it's then vented. So these kind of platforms always vent gas all the time. So we're expecting to see emissions from this guy. So this is the top-down view, and the drone was flown in that zigzag pattern, the slice through the methane plume. The wind is from the right here, so the methane plume is moving from right to left. So the drone was flown here in that slice, and we're looking down on top of it here. On the right here, this is looking at the same flight from the side as the data is plotted. So that was the drone flight path, and it's typically 30 to 40 meters away from the facility. So we don't get close to it into the zone, the hazardous areas. We don't fly over or anything. So you can fly quite far back and still see the methane plumes. This is a good example. So this is the field data, so the raw data. So the yellowy, greeny part is the background methane measurement, and the red part is the elevations above that, essentially. So this is plotted as it was acquired. This platform's got a vent stack up here, and this little plume we've picked up here is the vent stack emitting. That's the gas pneumatics running and emitting the methane. What we also saw on this particular platform was this huge methane plume, a substantial one coming from just below the main deck. This was a bit of a surprise to the operator. Obviously, they weren't expecting it to be emitting substantially. When this was analysed, the vent was emitting about 3 or 4 kilos an hour. This big one was about 65 kilos an hour, so a significant emission. Messed up all their reporting. The advantage of this is a direct measurement, so there's no disputing it, the existence of that plume. So it's a very positive way to say you've got a problem here. And we went back to the operator, and they looked at it, and they traced the problem. It was a P&ID problem, and then they were leaking out through the drain caisson. So they found the source of the problem. We went back and resurveyed it, and it was good. It was gone. But it's a good example of how a direct measurement like this can find unusual emitters that would be missed on a bottoms-up measurement. And 65 kilos an hour sounds like a lot, but you can't hear that, you can't smell it. It's leaking out steadily and slowly, but it doesn't show up as a leak in any of the systems or anything. So it's a big emission from an environmental point of view, but it doesn't show up on the safety systems. When we process the data, we extract the background, calculate what the background was, and remove that from the measurement, and then end up with these cross sections of the plume, kind of imaged by concentration. And this is the key input to the processing from a methane concentration into a quantification, how much methane is coming out. So that's what the end data looks like from a survey like this. You can visualize this data in different ways. Normally we would do a top-down image like this, high resolution, and drones are very good at that kind of stuff. So you can very quickly do a high-resolution image from the top, and then plot the data over that image like this, and that's helpful to see where that emission is coming from. You can track back, you can actually model back along the wind and see where that methane measurement came from, where that individual methane particle statistically came from. If you want to get a bit more sophisticated with it, the drone's equally capable of doing three-dimensional imaging. So you can fly and do a 3D image of your facility. If it's a big, complex one, and this is an FPSO in Australia, then it's very helpful to have that, and you can spin it around, and you can plot the methane emissions against that 3D image, and it's very helpful to see to see where they're coming from. And this example, this is the vent on the bow here, and you can see very, very clear, very, very big methane plume coming from the vent, kind of as expected. So as I said, drones are a good solution for Thailand because of the nature of the environment here. A lot of offshore facilities, a lot of onshore facilities, and drones are readily available. So as a solution, it's a pretty straightforward one to implement. There's a lot of good companies providing drone services. They're all using the same aircraft, but it's a mature market here, and the regulations are in place for drone activity. You still have to get a permit every time you want to fly, but it's pretty well established. So for agriculture, for oil and gas, other industrial applications, there's a lot of drone activity going on here. Offshore, there are some complexities because aerospace control areas don't match national boundaries. So you might fly in the JDA between Malaysia and Thailand, and it's under Ho Chi Minh City airspace, for example. So it becomes quite complicated when you get for permitting offshore. But it's getting better as the applications mature and the regulations get better. The authorities learn what we're trying to do. It's becoming easier to get those kind of applications. You can only fly to 90 meters without a special permission, but typically it's quite easy to get that permission to go up high enough so you can capture the flares and everything that you need to at that high altitude. I mentioned BV loss, beyond visual line of sight. That is possible in Thailand. The regulations are sophisticated enough that they are allowing BV loss in some applications. We're not quite there yet with offshore. Offshore, you typically use a fixed-wing drone, so an unmanned light aircraft, and that becomes a little bit more complicated in terms of how do you integrate that with civil aviation and so on. So not quite there yet with fixed-wing offshore, but onshore BV loss is a thing in Thailand. It can be done. One key environmental thing here is for all of these kind of technologies is because we're measuring a methane plume, that there has to be a methane plume there to start with. And the only way those form is if there is some wind to pick up the emissions from the source and carry them off into a measurable plume. And Thailand, a lot of places in this part of the world suffer from low winds in the summer, so it can be difficult to find a window to fly when there's enough wind to form a nice plume that's easily measured. And kind of counterintuitively, the measurement gets better the more wind there is. So at 1 to 3 meters per second it works, but at 5 to 8 meters per second it's significantly more accurate because the plumes become much nicer, much tidier. So I've got a couple of videos here just to kind of illustrate how this is done. So this is a case study from the southern North Sea in the UK. It's a Shell gas platform. It's a particularly nice summer's day for anybody who's familiar with the North Sea. It's not often like this. So you see this is obviously a boat-launched flight. Depending on the facility, you can choose to launch from the boat or from the helideck of the platform. The key thing is that the pilot can see the whole thing. So a boat is easier, but it's more complex and more costly. So in the front of the picture here, this blue thing, this is the methane sensor, and it's stuck out in front of the drone, so it's clear of the prop wash, so it's in clean air. In this case, the wind is coming towards us, it's towards the head of the drone, and you'll see they'll fly sideways back and forth because the wind is bringing the methane into the drone. It is possible to fly the drone with a sensor forward, but it's more inefficient because the drone has to rotate each time. So this is starting that zigzag pattern. They'll start at the bottom and go along, and you can see the altitude here is about 15 meters. So they'll tick along. Separation from the platform in this case is probably 40 meters. There's a couple of people standing up here, so you can kind of scale how far away we are. So they'll fly to the extremity of the zigzag, and then you'll see the altitude increase, and then the drone will fly back. And they'll do that enough times to cover the whole platform, and then they'll go back down, and essentially they'll do 4 passes to try and maximize the resolution of that image of the methane plume. So the drone itself is measuring the wind. This is a wind speed measurement derived from the flight control system of the drone. So we've got a calibration for that wind model as a helpful input to drive down that uncertainty in the wind component. So that's what it looks like. How am I doing for time, guys? Hey, couldn't it. How am I doing for time? Okay.
Last slide.
I haven't. Okay, I have time. I have another video, which is a nice one. I'll share it with you. So this is an onshore example, but this kind of shows what the drones can do, because this is all automatic, right? The drones are programmed with the waypoints, and they do this whole thing automatically. So this is an onshore location. And for these kind of sites, we'd normally do a box, because you get upwind sources as well. So if you're in a busy onshore location, there's going to be other facilities upwind, and there's a high chance that they're emitting, and that methane is going to be blowing down into your measurement area. So we do a upwind and downwind in those cases, so you can subtract anything which is leaking over from another site. So same kind of thing here. This is the drone's eye view, the sensor in the front, and in this case, the pilot will just program where the facilities are, where the different components are, and the drone will then just go ahead and fly it. So that automatic flight path is then recorded. So if you do work on the site, you do remediation or maintenance, you can then go back on another day, fly exactly the same flight path, and get a comparable measurement. So you can see it flies quite fast. These drones can fly for about 45 minutes with the sensor payload on them. So on a site like this, which has got like 4 or 5 different equipment components, then the whole thing can be done in one flight. And that data is taken back and processed. And that is my last slide. Yeah. So I think we've got a bit of time for questions. If anybody's got questions or comments, I'd be happy to take them.
All right. Got one question from the gentleman here.
Always. Thank you for the presentation. On your video, that sensor that is mounted on the drone, is the data for the detection live, or do you fly and then you get the drone back and download the data from the memory card, or the drone pilot would see where the emissions are coming and maybe try to change the flight path to...
Yeah, thanks for that. It's a great question. I should have mentioned it. So the drone pilot can see the methane data real time.
So that in your screen at the bottom, they would see that in the screen?
Yes, yeah, because the plume is quite dynamic, and if the wind shifts, then the pilot can adapt the flight on the fly to move the flux plane, the flight plane, to adapt that accordingly.
And then another question, is it just methane? Normally for like low pressure vents, you see methane, ethane, propane. Methane will be the worst one, but you just measure methane.
Yes, when we're looking at these very low concentrations, you have to have a very specialist sensor, and because methane is the big big bad guy for environmental perspective, that's the focus of pretty much all of these regulations, and hence the focus on methane specifically. We do have a CO2 version of this, which works in exactly the same way, but is focused on CO2.
Okay, thank you.
Thank you.
Thank you for the presentation. I have 2 questions. One is it mandatory for the measurements by any government in the world? 2 is like, if I have other measurements, when you measure, do you usually measure more methane, right? So let's say if I'm an operator, I buy satellite data, I don't see anything. So I can claim that I don't have methane. Why would I buy this more to show that there's more methane, I have to fix it?
Yeah, and you kind of, at the heart of that question is the fact that the regulatory environment everywhere is still very new, very young. So methane measurements themselves, as far as I know, are not mandatory anywhere, but reporting is mandatory in places like the US and the EU, increasingly the UK, North Sea. The reporting is mandatory, so you have to do some kind of measurement. And it's different operators have different strategies on how to meet that requirement, and it's not, typically these are not very prescriptive regulations, so they don't say you must use a sensor which measures down to 1 kilo per hour. It's still quite open for the operators to decide what their methodology is. However, as you get into regulations like the EPA in the US, where you're paying for your emissions at $900 a ton, then it's more important that you know exactly what you're emitting and you can report accurately so you don't overpay. And they're starting to become much more prescriptive on the technologies which are allowed to be used for that. And this is the kind of case where a satellite measurement wouldn't be acceptable because it misses half, at least, or more of the emissions. So for regulatory reporting off a particular facility, then satellites don't make the cut in terms of resolution. And so they would be disallowed by OGMP, the EPA, and so on. So you have to be prepared to measure at the site level rather than at the field level. Really, a satellite looking at field level. To get down to site level, you have to be looking at aircraft or below. I hope that answers the question.
Okay, thank you for a good talk. Thank you, appreciate it. Now, I'm kind of interested in the scales of magnitude here. Now, on one end of the scale, you've got cows. On the other end of the scale, you've got permafrost. Where are we? I mean, yeah, what's the elephant in the room here?
So, I read the number for a cow the other day, and I can't remember what it was. It was cows like 4 or 5 kilos a year or something of cow fart.
But there's a lot of fuss made of this.
Yeah, and there's a lot of cows. But so to give you some numbers, so the example there was the Southeast Asia example was 65 kilos an hour of an unexpected emission, 3 to 5 kilos an hour of expected emission. And for a facility like that platform, it's new, it's got a gas pneumatics, 3 to 5 kilos an hour is normal. For a big offshore CPP, like Bangkok there, and we haven't surveyed it, you'd be looking at maybe 60 to 70 kilos an hour. But the most of that would be coming from the flare and from the gas turbines.
Right, now I appreciate the title of your talk, Offshore Facilities, but you've avoided the permafrost issue. What is the volume we're talking about here? Say Russia. How much are we talking about here?
Good question. That's outside my area of expertise, but obviously that's a massive potential source of methane emissions if that starts to melt faster.
It must be massive.
Yeah, that's an environmental tipping point. If that starts to melt and release that methane, then this becomes probably moot.
Okay, thank you.
Thank you.
Hello, sir. I'm student from Chulalongkorn University. Thank you. I wonder how do you minimize the error of the methane content when you fly in the zigzag pattern? So let's say that the content of the methane vary with the altitude. How did you minimize the error from when you do the measurement?
That's a good question again. A few different ways. The gas measurement itself, the concentration measurement itself is very precise, and we can see the data from the laser. We've got control of the data from the laser, so we know the uncertainty in that actual concentration measurement. And then to maximize or minimize the uncertainty in the flight itself, the automatic flight path is very valuable because the drone can fly to within a couple of centimeters of where it's told to, so very precise flight paths. And then flying the cross paths through the methane plume as densely as possible allows us to capture the highest resolution snapshot of that methane plume. Depending on how big the facility is, we might need to stretch things out So the flight path is bigger and less dense, and that does drive down the accuracy of the methane concentration. At the expense of accuracy, you get a much bigger measurement. And then the real-time visibility of the data allows the pilot to optimize it. So we try and make sure we've captured the whole lot and not cut off one edge or anything. So a lot of effort is paid to make sure we've got 100% coverage of that emission. So that covers the question.
Any questions?
Any more questions from students?
A question, I'm sure your data set's improving with time, the more and more offshore facilities, onshore facilities you look at, you've got a very good understanding of the sources. How about the mitigation? What are your insights on the mitigation measures that can be applied to reduce the methane emissions?
Thanks for that. And so we report our emissions findings to the OGCI, the Oil and Gas Climate Initiative, so that they oblige us to report what we do. And they try and get us also to report the mitigations, because we typically repeat surveys. So we'll go back and resurvey sites on a regular basis. So we should be able to see the results of mitigation efforts that the owners have done. And the OGCI uses a kind of general factor of 65%. So they assume that if we measure an emission, the reduction in emissions after mitigation is 65%. That's a bit of a debatable number, because it obviously varies substantially depending on the operator, depending on how careful they were, facility to facility. But that's the best data we've got, and we do see it happening. Just again, putting some numbers on it. Last year we measured this 475,000 tons of CO2e, sorry, of methane, which is about 4.5 million tons. Sorry, I'm getting my barrels mixed up. So 475,000 tons, which is about 7 million tons of CO2 equivalent. And so if you take the 65% of that should be the mitigation. Difficult for us to get reliable data back. Operators tend to be quite canny about what they've done. So they, especially if the emissions are higher than expected, they tend to be quiet about the mitigations.
Perhaps one more question, last one, if you may have.
One last question from another table of students. Maybe.
Otherwise, thank you for your good presentation for tonight.
Good. Thanks everyone. Appreciate
Thank you very
it.
much.
Appreciate the questions.
Please give a round of applause to Dave Turner.
Okay.
Okay. I'm MC.
I call him too. Okay. All right. On behalf of SPE Thailand, we'd like to summon Kun Anupong to give the token of appreciation to our speaker for tonight.
No, MC, definitely.
MC cannot call himself, so.
So let's go for the closing remark for tonight. Okay, I would like to make the more announcement for the next meetings. On 21st of March next month with John Sakovic, which is joint SPE Thailand AIEN monthly technical meeting in the topic greenwashing and ESG, what you need to know, right? And also, we would like to announce that we, SPE Thailand, we contribute to our society and especially student chapters. We have annual the scholarship program, which we already given the scholarship to our students from various universities. And also followed by let's say notifications or for the ENP award this year. The abstract submission deadline is last day of this month. We still have time. If you or your company has the good project in last year or 2 years time, please remind your team to submit the abstract to our SPE. Right? And the rest of the SPE Asia Pacific upcoming event. Right? The main event this month is going to be Offshore Technology Conference Asia at Kuala Lumpur during 27 February until 1st of March. Right? You can follow by the rest of the workshop and symposium on the SPE website. And also SPWLA Bangkok chapter on 29 February, right? The speaker, Mr. Douglas Hartman, right, on the topic Beyond Triple Quad Combo Nuclear Magnetic Resonance, Dielectrics and Spectroscopy Locks, right? Next one, the grand event AIEN, International Energy Summit, during the June 11 to 13. There are keynote speakers from PTTEP, Petronas, and Vela Energy. Last but not least, SPIADC Asia Pacific Drilling Technology Conference and Exhibitions during 7 and 8 August and hosted by PTTEP. Okay, and another one. Oh, we have a lot of events this year, actually. SPWLA Bangkok, right, 6 to 9 October. Still call the abstract to present in the conference. Okay, our section needs you to get connect. We have many options to get update for our event, right? Facebook page, LinkedIn, and Line official, and also YouTube SPE Thailand. You can see the live record on our SPE YouTube channel as well. Okay, lucky draw time. I would like to introduce Dave to pick up the lucky draw.
So the lucky draw for tonight, I believe you've got a lot of work to do. Sometimes one keyboard may not be enough, so we will give you another one. Probably make your job faster. With Mickey Mouse and Minnie Mouse theme on it.
Okay, so the lucky winner of the pink keyboard is Santaya from Rystad.
Good Santaya. All right. Mickey Mouse. We have two color choice for you. We have pink, oops, and purple. You want purple one? All right.
Purple one.
Not too girly. She won this one.
Thank you so much.
Congratulations.
Thank you.
Okay, look at the camera. 1, 2, 3.
Thank you.
Okay, next one.
So the lucky one for tonight with the pink Mickey Mouse keyboard and mouse set is.
So the lucky winner of pink is Chow Yong from Chulalongkorn University.
All right. Student.
Congratulations.
Now you can work on your thesis. In pink as well.
Can you read the name again?
He's there, he's here.
Chawin. Oh, you are. All right.
Okay, look at the camera. 1, 2, 3.
Congratulations.
All right, and this is a before last page for our sponsor logo. Please give an applause for this logo as well. Thank you. And last one. Okay, no. 241 promotion downstairs. Thank you for your time for tonight and have a good night. Thank you.